Okay, now question 3. It says, to what temperature would you have to cool the diver to produce the same change in the volume of air in her lungs? Assumed temperature initial is 27 degrees Celsius. Answer in units of degrees Fahrenheit. Okay, now we're going to have to do some conversions, of course, because we have Celsius, Fahrenheit, and for ideal gases, we work with Kelvin. Now, let's start with the given. As you can see, there is not a lot of explicit given, just the temperature initial, which is 27 degrees Celsius. Now, they say they want to know the temperature, so we're trying to find temperature, to produce the same change in volume, meaning you're going to have a difference in volume, in this case, final volume, initial volume, which we can get from question number 2. It says we got volume initial to be 6.0 liters, and the final volume is 3.05 liters. Now, for question 2, the temperature was held constant. In this case, we have to change the temperature, which means the pressure will be constant. Okay, so pressure initial would be the same as pressure final, which is simply pressure P. All right. And we need to find final temperature. TF equals, we don't know. We have to be creative. So we start with the ideal gas equation. PV equals NKT. Now, the initial conditions, not equal, should be proportional. Okay, proportional to the final conditions. Now, pressure is going to be constant. Number of molecules is the same for both. And Boltzmann's constant, well, is a constant. Based on this, we can come up with the ratio, which will say volume initial divided by final volume should be equal to temperature initial divided by temperature final. Okay, now we need to solve for temperature final. So let's do very simple algebra, multiply temperature final on both sides. This cancels, so we have temperature final times volume initial divided by final volume equals temperature initial. I'm trying to find the final temperature. And since we do not have a numbers dependency, I can treat that fraction with letters as a fraction with numbers, meaning I can just multiply by the reciprocal to get rid of it. So times final volume divided by initial volume. Notice how I am just flipping that fraction. So let's write it down over here, 2. And we have an equation, we have a formula for, or not a formula, just an equation, because it applies to this problem. There you go. Now before we substitute, we should convert our temperature to Kelvin, because for ideal gases we use Kelvin. And we know that temperature in Kelvin equals temperature in Celsius plus 273. In this case, temperature in Kelvin will be temperature in Celsius, which is 27 plus 273. That is 300 Kelvin. There you go. Now we can substitute. Temperature final equals temperature initial, that is 300 Kelvin, times final volume. Let me get some more space. That'll be 3.05 liters divided by 6.0 liters. And 3 divided by 6 is 1/2, so I should get somewhere around 150. So let's do that real quick. 300 times 3.05 divided by 6, 152.5 Kelvin. So temperature final, 152.5 Kelvin. We're not done. Now we have to convert to Fahrenheit. You can do it directly, but my suggestion is convert to Celsius and then to Fahrenheit. So we know that temperature in Celsius equals temperature in Kelvin minus 273, meaning our temperature in Kelvin would be 152.5 minus 273 minus 273 negative 120.5. That is the temperature in Celsius. Now let's convert to Fahrenheit. Switch to blue. So the formula is temperature in Fahrenheit equals, let's try that again. Come on. Much better. That is 9 divided by 5 times temperature in Celsius plus 32. Let's substitute temperature in Fahrenheit equals 9 divided by 5 times temperature in Celsius, negative 120.5 plus 32. We're going to multiply this times 9 divided by 5, and then add 32, 184.9. So let's round it 185, negative. So the temperature in Fahrenheit is negative 185 degrees Fahrenheit. Let's box it. There you go. Next question. Okay, it says, at the depth of 10 meters, the diver breathes in air from a scuba tank, filling her lungs with air whose pressure equals that of the surrounding water. How does the number of air molecules in her lungs compare with the number she had in a full breath at the surface? Okay, so now we need to compare the number of molecules from the ideal gas equation, that is the letter N, capital N. And then we have a hint. Think about the ratio from pressure at sea level to the pressure at 10 meters under sea level and its relationship to the number of molecules. Okay, so let's write down what we know from pressure at the surface and pressure at 10 meters. So pressure at the surface at sea level is 1 atm. So we're going to call it pressure initial. Now, look, actually, we have to, since we're starting at 10 meters, now 10 meters will be the initial pressure. And now we're changing the initial conditions. Now we're starting 10 meters under sea level. So pressure initial was our pressure final. So that's the one we got on problem number 2, 1.97. And then our pressure final is at the surface, which is 1.0 atm. Okay? So now we have to find the number of molecules. So number of molecules, well, the ratio. The ratio would be number of molecules initial divided by number of molecules final. That is the ratio, and that is what we're trying to find. Okay. Now, we can do proportionality, right? Because of the ideal gas law, just like we did on question 3, where they're proportional, we can say pressure initial divided by pressure final equals number of molecules initial divided by number of molecules final. Now, the reason why I can do this is we established the initial conditions for the ideal gas law are the same as the final conditions, but they're proportional to the final conditions. In this case, we're changing the number of molecules. Okay, that's why we're able to do this. And we know that pressure initial divided by pressure final is the ratio, right? The ratio of number of molecules, which is what we're trying to find. And now it's very simple. Pressure initial, 1.97 atm divided by 1.0 atm, that is 1.97 because the atm's cancel, and that is the ratio. So about 2 times the number of molecules, so twice as many. Let's box it instead. There you go. Y'all making fun of me?
Yeah.
That's cool. Alright, let's see how it is. So question 5, I'm going to hurry up before they keep making fun of me. Now we have the same situation. Depth of 10 meters, the diver breathes from the scuba tank, filling her lungs with air, whose pressure equals that of the surrounding water. So same situation. Then she's going back up to the surface, holding her breath. When she reaches the top, find the excess pressure of the air in her lungs. Now, excess pressure, that means we need to find a difference. Difference is subtraction, right? And the volume will be 6 liters because it says we're going to assume we can't expand more than that, okay? So this is very simple. I mean, you can do the PV equals NKT, or we can remember that the difference in pressure is pressure final minus pressure initial. Now, what's changing is the conditions, meaning now we're starting at the bottom, well, not the bottom, but 10 meters under sea level, meaning we start with the greater pressure. So from questions 1, 2, 3, our final pressure is going to be our initial pressure, just like we did on question 4. So pressure initial, that is at 10 meters, is 1.97 atm. Pressure final, we know at the surface, it'll be 1.0 atm. So now, we can do the very simple arithmetic, which is pressure final, that is 1.97 atm. Nope, the other way around, sorry. 1.0 atm. That is the final pressure at the surface. She started with 1.97 atm of pressure. So the change in pressure is negative 0.97 atm. So that is the excess pressure, about 1 atm. Now I'm going to say let's box it because they're going to make fun of me, but I just said it. So 1 atm more. Again, we just found the difference in pressure after flipping the conditions. Now, 1 atm is a lot of pressure. So the last question is asking you, what's going to happen? Well, let me put it this way. If you have an increase in pressure in the lungs, think of them as balloons, right? So if they're already at max level, that is the 6 liters, if you keep adding air, so if you keep increasing the pressure, that excess pressure, since the air cannot go anywhere else, but the balloon would pop. So now try to relate that to what would happen to the poor scuba diver. That one I'll leave it up to you. That's it.